Is it Austin? I'm Professor Brian Evans. This is W445S Real-Time Digital Signal Processing Lab for the spring 2014 semester. This is Lecture 6, Part 4. So Lecture 6 is on infinite impulse response filters. And so far we've talked about the many roles for filters. This is for spectral estimation, spectral analysis, and spectral shaping. We've talked about two IIR filter structures. We've talked about the biquad, which is two poles, and 0, 1, or 2 non-trivial zeros. This is the basic building block for infinite impulse response filter implementation. We'll talk more about that today in Part 4. We talk about direct form implementation, which is to implement an IIR filter as one section, one filter section, where we expand the poles and zeros into feed forward and feedback coefficients. We can use that form to reuse an FIR implementation, which I'll talk about today as well. Talked about bounded input, bounded output stability, and for our purposes, that means that the poles have to be inside the unit circle for a causal, linear time invariant system to be stable. We talked about the connection between Z and Laplace transforms, and we talked a little bit about cascaded biquad implementation and quality factors. Okay, so today we're going to move on into looking at, again, cascaded biquads in more detail. We'll also look at how to implement an infinite impulse response and a finite impulse response filter on a digital signal processor, and we'll use the C6700 family from Texas Instruments as an example. So on to Part 4. Okay, for IIR filter implementation, there are many, many different ways to do this. One of the big reasons is to try to ensure that the implementation remains bounded input, bounded output stable. So in theory, we start with our poles inside the unit circle for our causal implementation. And after implementation, we'd like to make sure that those poles remain inside the unit circle after we decide on what data format we want and what coefficient format we want. In this particular class, we're looking at a couple different formats. In the laboratory, we're looking at 32-bit floating point. In MATLAB, we're looking at 64-bit floating point. But more generally, we may be in 16-bit integer or short int. We want to make sure that our filter works properly without going numerically unstable on us. Okay, so for IIR filter implementation, there is a similar approach in both discrete time and continuous time. And what is the same approach is to take our transfer function and break it into pairs of poles, and each pair of poles becomes a biquad. A biquad here is just another word for second order section. Biquad means biquadratic. That is to say the transfer function is a ratio of two quadratic polynomials. So in classical IIR filter design, which is very useful as a starting point, we get filter order here that is either odd or even, and the filter order means the number of poles. So in the case of an even order filter, so I'll just read it. So filter of order n will have n over 2 conjugate roots if n is even or one real root, and n minus 1 quantity over 2 conjugate roots if n is odd. So if we have an 8th order filter, it means I have 4 pairs of conjugate symmetric poles in my IIR filter. If I have, let's say, a 3rd order filter, then I would have 1 biquad and 1 1st order filter. If I have a 5th order filter, I have 2 biquads and a 1st order filter. And the response of the filter is very sensitive to pole locations. And once we implement the filter in a particular data type, for example, 32-bit float or 16-bit short int, then the pole locations will be perturbed. We will not, in all likelihood, be able to exactly represent them. And so this perturbation in the pole locations is a problem. It can lead to numerical instability if we don't do this carefully. So if I have a cascade of, let's say, a third order filter, the question is, okay, I have a biquad, which is a second order structure or section, and a 1st order filter. And if I have a 3rd order filter, one of those pole locations will be real valued, and the other 2 pole locations will be complex and conjugate symmetric. And the question is, well, what order do I choose? So there's a rule of thumb for implementing IIR filters, And that rule of thumb is to decompose the IIR filter into second-order sections. And if we have one, we may also have a first-order section, but only one first-order section if we have an odd-length filter, odd-order filter. So we want to cascade the biquads from input to output in order of ascending quality factors. So we talked about quality factors in part 3, so just to review what the quality factor means. The quality factor is a technology-independent measure, so we're not worried about, are we going to implement this in 16-bit fixed point or 32-bit floating point when we compute the quality factor. Instead, it gives us an idea of how sensitive the pole locations are, or the pole pair is, to oscillation. So this was from, again, lecture 6, part 3. For if we have pole locations here that are conjugate symmetric, then we can define a quality factor, which is described here by a fairly complicated-looking equation. This quality factor takes range from 1/2 to infinity. 1/2 is included and infinity is not included. And if we look at the terms in here, so we have poles at a plus or minus jb, so they're conjugate symmetric. We can also write them in polar form with a radius and a phase, so radius r or magnitude r and phase theta. And again, the magnitude is just the Euclidean distance here, so it's the sum of the squares of the real and imaginary components. And this is the pole radius, and for bounded input, bounded output stability, we want this radius to be less than 1. We have another term that's just convenient to make it easier for the equation to have fewer terms in the equation, which is y is minus 2a. And this is, a is here again the real component of the pole location. So if we put this together, there's a fairly complicated formula here for the quality factor, but there's some very important things we can pull out of this. One is for real poles, that is to say when b is 0, when the imaginary component b is 0, and we know that a has to be in a magnitude between minus 1 and 1, but not inclusive for bibo stability reasons. We know from this that the quality factor, if we just put these terms into the equation, gives us a quality factor of 1/2. Okay, so this is very important. It means that this quality factor of 1/2 corresponds to the case where I don't have oscillation in the impulse response. So here's the impulse response. So provided that A here, actually, to be more precise, if you look at this, this is just decaying exponential and another decaying exponential times n. So there's no oscillation unless A happens to be a negative real number, then we alternate 1 minus 1, 1 minus 1. If A is a real number, then we have no oscillation whatsoever. We just get exponential decay as n increases from 0 to infinity. Now, the other extreme case is poles on the unit circle. For poles on the unit circle, the radius is 1, and we're no longer bibostable. If we look at the Q function, and we take the limit as r goes to 1 of the Q function, then we can see that in the limit, as r goes to 1, the quality factor goes to infinity. Now, poles on the unit circle means that we have an oscillation in the impulse response. In fact, the impulse response is a pure oscillation, provided theta is not 0. It is a way to generate a sinusoid. So this location for poles on the unit circle gives us an excellent oscillator, but a terrible filter. For a filter, we don't want to generate new frequencies. We want to pass, attenuate, or reject existing frequencies in the input signal. We don't want to generate new ones. So we do not want to have a very high quality factor in our filter section, in our filter pole locations. Now, this is a fairly complicated formula. That is to say, this quality factor is a fairly complicated formula. And I covered these other two cases. I covered the case of imaginary poles in lecture 6, part 3. What I do want to say is once we know the quality factor of each pole pair, or if it's real, we know it's going to be a quality factor of 1/2, then I also have an idea of what target implementations are practical given this quality factor. And in particular, I want to look at the maximum quality factor of all the pole pairs to figure out what's my worst case, which pole pair is most likely to oscillate after implementation. And so for a rule of thumb, this next one is now just from experience, and it's somewhat ad hoc, but For a 16-bit fixed-point DSP, this is a more conventional DSP, but also the C6000 also can be used in this mode using its integer arithmetic, integer multiply, and integer add operation. So for a 16-bit fixed-point digital signal processor with 40-bit accumulation or addition, then about the maximum Q we can support is about 40. So the quality factor is really useful in, once you have a filter design, how do I determine the order of my biquads, or if I have an auto order filter, where does the real pole go? It can also be embedded in a design formula. What's more common in the design formulas is not to include the quality factor, but instead to use something very similar, which is to, as I have here highlighted at the bottom of the slide, is to instead use the pole radius as an approximation of the quality factor. So we see that, you know, as the radius increases, the quality factor, as the radius goes closer from 0 to 1, as the radius increases from 0 to 1, the quality factor can increase. And once we get up to r equals 1, we get a quality factor of infinity. So we could, instead of embedding the quality factor in the design, which we could do, a more common approach in filter design software is to limit the pole radius, or the radii of the pole locations, of all the poles that the filter design algorithm gives us. So you find this in MATLAB, you can find this in LabVIEW and other filter design algorithm implementations. So we can just simply constrain the radius of the poles to, say, less than 0.9, or 0.92, or 0.88. I'll have demos of this in Lecture 6, Part 5, to follow this one. Okay, so you can do constraint optimization using, by limiting the radius of the poles. You could also, likewise, do constraint optimization by limiting the maximum quality factor to a particular number. You can do it either way. Okay, so back to our kind of kickoff slide here for Lecture 6, Part 4, is that, back to our rule of thumb. So our rule of thumb for implementing IIR filters is to decompose the IIR filter into second-order sections. So a second-order section is also a biquad. As to say, second order means here two pole locations that are non-trivial, let's say not zero. And we're going to cascade so we want to cascade an implementation. We'll cascade the biquads from input to output in order of ascending quality factors. So if I have a third-order filter, then I have, so here's an example. So take a third-order filter. The third-order filter has a real pole and a pair of conjugate symmetric poles. So I have one biquad and one first-order section. And the question is, where do I put the first-order section? Do I put it before or after the biquad? And we know that for a real valued pole, the quality factor is 1/2. It's the best situation we could be in, and so we like to put that first. So in terms of implementation, again, this is a rule of thumb. It's not necessarily the optimal answer. It's just a way to get a filter structure quickly from a list of pole locations that makes sense. It's not necessarily the best way to do it. It's a rule of thumb. So here's the first order filter goes here to start things off. Here's my first order IIR. And we'll feed that into, so my input is X, output is Y. So we'll feed the first order into second order, the biquad. And then here's the biquad. And the output of the biquad is the output of the entire third order system. So there's my third order filter. That's the third order case. Now for the fourth order case, then now the question is, which biquad do I put first? Well, again, for the third order case, we know we want the first order first because the quality factor is 1/2. So the quality factor is 1/2 for a first order filter section with a real pole. Again, for our discussions, our assumption is that the input signal is real valued, the output signal is real valued, and the coefficients of the filter, if we looked at feed forward and feedback coefficients, would be real valued as well. And one of the reasons for, again, having real valued coefficients certainly makes the computation easier than doing complex arithmetic. However, there are some cases where the feedback and feed forward coefficients might be complex valued. We'll see that later in the class. That does happen. But for now, everything is going to be real valued in terms of feed forward coefficients, feedback coefficients, input signals, and output signals. That also means that the poles and zeros are not necessarily real valued. Either they're going to be real valued or they're going to be in conjugate symmetric pairs. We talked about that earlier in Lecture 6, Part 1. Okay, so let's move on to the rest of this slide. So now the question is, if I have a fourth order filter, I now want to pick the order of the biquads from input to output in order of ascending quality factors. So I can apply the same idea. And if the quality factors are identical for the two biquads in the order, by this rule of thumb doesn't matter. Now this is a rule of thumb. This tells us how to choose the pole locations in which order they're going to go into the filter structure. But it doesn't tell us yet how to assign or associate zero locations with pole locations. So as a rule of thumb, another rule of thumb is that for every pair of poles in a biquad, we're going to pick, for each pole, we're going to pick the zero that's closest to it. Again, this is a ad hoc rule of thumb just to get us to an answer. All right, now let's talk about classical filter design. This is very common. So classical filter design has been around a long time, in analog continuous time, I think back to the 40s or 50s. Been around a very long time. The classical infinite impulse response filter designs differ in the shape of their magnitude responses, and they also differ in the number of pole locations needed to meet a certain magnitude response specification. So Butterworth gives us monotonically decreasing magnitude response versus frequency. There's no ripple in either pass band or stop band. So the Butterworth magnitude response, I'm just going to draw it in continuous time frequencies, might look like this. So it's monotonically decreasing. This is in linear units, the way I've drawn it. So as frequency increases, the magnitude response is monotonically decreasing. There is no ripple. For Chebyshev type 1 and 2, there's ripple in pass band or stop band, but not the other one. So Chebyshev type 1, we monotonically decrease. So here's the Butterworth. Just write that down. So for Chebyshev type 1, we monotonically decrease in pass band, but have ripples in the stop band. So again, the magnitude response monotonically decreasing in the pass band, and then we get ripples in the stop band. So that's Chebyshev. Then Chebyshev type 2, we've got ripples in the pass band, but not, and monotonically decreasing in the stop band. There's Chebyshev type 2. And then finally, the equal ripple design is the elliptic design. This has ripples in both passband and stopband. So equal ripple and the same ideas hold in discrete time frequencies as well. Okay, so this equal ripple design in the IIR case has an analogy in the finite impulse response filter design case. In the finite impulse response filter design case, the equal ripple design was the Parks-McClellan algorithm. Now, underlying the two designs are different sets of polynomials. The elliptic uses Jacobi elliptic functions, and the Parks-McClellan uses Chebyshev polynomials. So that's different. But what is the same is that we get ripples in both the passband and stopband. Another big difference is that these algorithms for classical IIR filter design are not iterative. These are closed-form formulas. So the classical IIR filter design algorithms use closed-form formulas. They do not iterate to find the pole zero locations. Instead, they have formulas for the pole zero locations. Now, what's also important is that means that when you use a classical IIR filter design algorithm, you get back a list of poles, a list of zeros, and a gain. Or you might get it back in second order sections, which is a list of, for every biquad or every section, a list of the poles, zeros, and gain. Okay, so MATLAB, for example, has a second order section format with this data structure. And what you'll notice here is that these classical IIR filters have poles and zeros. Excuse me, and by zeros I mean here non-trivial zeros. And one exception is the continuous time low-pass Butterworth filter. They only have pole locations. And all the zeros are trivial. That is to say, they're all at the origin. Classical filters, unfortunately, are easy to design. The formulas are straightforward to implement, which is nice. Not so easy. Those formulas are hard to derive, but people derive them. Once they've been derived, the formulas are pretty easy to implement in a piece of software. The bad news is that these classical filters give you biquads with very high quality factors. So it turns out, although very easy to use as design formulas and implement, they give us pole locations that have very high quality factors. That is to say, they're prone to oscillation, and therefore make it a little bit difficult to implement. Okay, so let me go back one. So what we can do in the classical case is pick our first approach to implement an IIR filter would be get the pairs of conjugate symmetric poles, and then put them into biquads in ascending order of quality factors, and then for every pole location in each biquad, take the closest zero from the list of zeros to be associated with that pole location in that biquad. So that's a very straightforward rule of thumb to use. The better approach, if there's more time, is to try all combinations that are possible. So if I have a second order filter, there isn't really any option. I just have two poles and up to two non-trivial zeros. There's just one biquad. If I take a third order filter, as I had on the previous slide, then what I can do is I have two choices really on the ordering. I have two choices on the ordering. Oops. Right, so I can either go with and so the rule of thumb would say use the first order filter first and then the biquad, but really to be exhaustive, I should try the other order as well. I also have three non-trivial zero locations, and I should really try all possible combinations. So if I have one pair of conjugate symmetric zeros, then that's going to go in the biquad. If I have a real zero, it's going to go in the first order section. If I have if I have a fourth order filter, now I have two biquads, I have two choices. And then I also, for every biquad, I have two choices of conjugate zero choices. So now I have 2 times 2 possibilities. I have 4 possibilities for all possible permutations, and I could simulate all 4 possibilities in software, either in some fixed point toolbox, for example, in MATLAB for discrete time, or if it's continuous time analog, I could do SPICE simulation to figure out which is the best way to go. Now, it gets more complicated with higher order filters. If I have a 6th order filter, let's think about 6th order filter for a second. So for a 6th order filter, I've got 3 choices. So I've got, for biquad choices, I have 3 pairs of conjugate symmetric poles. So I have 3 possible choices of the first biquad. I have 2 possible choices of the second biquad. I have 1 choice remaining on the third biquad as far as pole locations go. For each choice of the first biquad, for the 3 choices of the first biquad, I've got 3 different conjugate symmetric pairs of zeros that I could pick one of them to put in this biquad. So I have actually 3 choices for the first biquad in terms of pole locations, but then for each pair of conjugate symmetric poles, I have 3 choices of conjugate symmetric zeros to choose from. So I end up with 3 times this, and then 2 times this. So I end up with this essentially squared. So in terms of biquad, for pole locations, I have 6 choices. So I have 6 choices of pole pair locations. And for every choice of pole pair locations, I have 6 possible, so I have 3 possible choices of conjugate symmetric zero locations. So I suppose I can multiply by 3 times this to get the number of actual choices. Now this gets more interesting when I have a 10th order filter. Now I have 5 factorial possibilities in how I arrange my conjugate symmetric poles. And then I have times 5 possibilities for each one of those, which pair of conjugate symmetric zeros that I use. So this grows very quickly with the order in terms of how many permutations I have to explore to find the best one. So I need to, and so for every possible filter structure that I could, for every possible filter permutation here, I would run a set of test signals through, perhaps noise, perhaps sinusoids, and other test signals, and look at how close the output is to what I'd like to have given the magnitude specification. And that would let me pick my best choice. Okay, so I created some software a long time ago, back at 95, 96, and published some papers on this. So what I did here is integrating the quality factor into the actual design procedure. So I start with an existing classical design. I then allow the user to decide, what else do you want me to do with moving the pole and zero locations around? I want to keep the magnitude response within the specification, but I might also want linear phase in the passband, a low peak overshoot in the step response, and I may also want to control the size of the quality factors to be less than some number. So just to give a very simple example of this, although it's in continuous time, here's a very simple low-pass infinite impulse response filters design specification. It's low pass band's at 20 radians per second, the stop band's at 30 radians per second. It's a very mild design here. This is in linear units, not dB. Pass band is 0.21. The stop band attenuation is 0.31 in linear units. I also told the software this is basically Mathematica derivations that generates MATLAB code. So I minimize deviation from linear phase. I minimize the peak overshoot in the step response. And I limit the maximum quality factor to be 10. So I start with the classical design, which is shown in the lower left. It meets the magnitude specification. The problem is the quality factor of the second section is 61. And if you remember from Lecture 6, Part 3, this is higher than I can reasonably implement with passive components. The max Q is around 40. And this would be resistors, inductors, capacitors. It's also above what I could do in switch capacitor. That's about 60 for max Q. Excuse me. So what I can do is run the software to lower the maximum Q, still meet magnitude spec, and also do some other nice things. So in running the software, first of all, I get the quality factors down to something that's easier to implement. The max Q is 10. Still meet the magnitude specification. I also, over the passband frequencies, make the phase response close to linear, which is a bonus. And I also decrease the peak overshoot. So this point right here is 1.0. So the peak overshoot is dropped by about 50% from 16% overshoot to 8% overshoot. This would be in the step response. So again, the elliptic filters in the dotted lines, the optimized filters in the solid lines, and this takes less than a minute to run in MATLAB. So you can integrate the quality factor definition into your filter design software. And whether you do or not, you can still use quality factors to guide you in how to order the pole pairs in biquads in a cascaded implementation. Okay, so I'm going to save the demos here for Lecture 6, Part 5. What I'm going to do now is switch to a handout in the course reader. This is Appendix N. This is how to implement an FIR filter on a digital signal processor, but the idea also applies for IIR filters as well. We can reuse the same code to do that. Okay, again, this is Appendix N, as in Nancy or Nick. This is in the course reader and also available online. All right, so this is a handout that talks about the computational complexity of implementing a tap delay line on the C67 digital signal processor from Texas Instruments. This is a floating point processor, but it also does fixed point integer arithmetic as well. What we'd like to implement is we'd like to compute one output sample, y of n, of a finite impulse response of n coefficients. Those n coefficients of our impulse response are h0, h1, all the way up to h of n minus n, capital N minus 1. So for every input sample x of n, we need to compute capital N multiplications and capital N minus 1 additions. So here is the input-output relationship of our finite impulse response filter for input x and output y. It's really just the convolution of the input signal and the impulse response. We talked about this quite a bit in Lecture 5, Part 1. And also in Lecture 3, Part 2. So anyway, this is our difference equation. This is really a difference equation. We want to just compute. We want to do one multiply and then follow it with an add. Multiply, add, multiply, add. So there's a structure that we can take advantage of in the implementation. On this particular handout, we're going to do the implementation in single precision floating point arithmetic, 32-bit coefficients. We'll also assume that the data, the input data x of n and the output data y of n, is also stored in this 32-bit floating point format that follows the IEEE standard. Now, one of the drawbacks we hit right away on the 6700 is that the 6700 has two. And each data bus is 32 bits. Normally not a big deal, but now, for every time we want to do a multiply, I have to do 2 reads. I have to read H naught and X of n. But on the 6700, I only have 2 data buses, so I have to spend an entire instruction cycle in terms of read-write operations. Excuse me, I can only read in one cycle H naught and X of n. I can't read any more than that. So that's my bottleneck. So in order to, and this is what I can read in from local on-chip memory into registers. And I can't do any mathematical operations on these values until I get them into registers. So I move them into registers, and then I can multiply and add, multiply, add. But it's limiting because the only way the speed at which I can multiply is limited to how fast I can get the data into the registers in the CPU core. So even though I have 2 multiply units on the processor, I can only put 1 to use at a time because I can't feed the 2 multipliers fast enough. I can only feed 1 fast enough. There's some other issues here. The processor is intended to run it up to very high speeds. The clock speeds max out at 1.5 gigahertz, and they started down around 200 megahertz. So this is a pretty wide range of clock speeds. So when they put this processor together, they went ahead and decomposed complicated operations into multiple instruction cycles. And this allows the clock to scale better. It also allows faster calculations of simple operations like logic operations like logical AND, bitwise AND, bitwise OR, exclusive OR. So the load command, which is how we're going to get data from on-chip memory into registers, has a 1 cycle of throughput, which is great, but then we have to wait 4 delay cycles for the data to be finally ready in the register before we can use it. Also, it turns out the multiply single precision command on this processor has 3 cycles of delay and 1 cycle of throughput. So again, every time we issue a multiply command, we have to wait 3 additional cycles before the result is ready. And it turns out also the add single precision operation also requires 3 delay cycles. So we have to, once we issue the instruction, we have to wait 3 cycles for the result to be ready. So let's look at the code for this, and the code to realize this difference equation is I have it in sort of pseudocode and assembly combined. I don't allocate registers just to make it easier to read. And that has to be done in a separate step. Also, to make it easier to read, I don't use any looping, although I certainly could. So this particular code would only be useful if I really knew how long the FIR filter was. If I knew capital N, the number of coefficients, in advance, and that number N is a constant. For a more general approach, I would use a for loop. Okay, so let's look at what we have to do. So I have to get this started, I want to first load in the current input value, X of n, and I'm going to load in the first coefficients, H naught. Now I have to wait 4 delay slots, 4 cycles before that result is ready. Those results actually are ready now in registers. And you'll see that in the next bold instruction. So I have to wait 4 cycles before I can do any work, before I can multiply H naught and X of n together, because I have to wait 4 delay slots before those values have been read in from local on-chip memory into registers in the CPU core. By the time we get to, so load command has got 4 delay slots, so by the time we get to cycle 6, the data is ready at the beginning of cycle 6 or between cycles 5 and 6, and now I can multiply the register containing X of n and the register containing H naught to produce product 0. Now the multiply command has 3 cycles of delay, so before I can take the result of the multiplication and add it to the previous multiplication operations, I have to wait 1, 2, 1 cycles before I can start adding the product to whatever I previously added. Now, to start with, I haven't added anything. So initially, the accumulator is 0 that I'm going to use. And I'm just going to keep adding to that every time I do a multiplication. Now the problem is that when I do the addition, I have to wait 3 cycles for the result to be ready, and so I cannot add anything to the accumulator 0 until this add single precision has completed. That won't be completed for another 3 cycles. So I can't use the register holding accumulator 0 until cycle 14, which I do down here. Now, what I could do if I were inefficient is just not do anything in the meantime. So while I'm waiting for X of n and H0, H0 to be loaded from on-chip local memory into CPU core registers, I could decide just to be idle and not do anything, but that wouldn't be very efficient. So what I do on cycle number 2, excuse me, is I read in the previous input value in coefficient H1, and I have to wait 4 cycles before that data is ready in the CPU registers, in the CPU core registers, 1, 2, 3, 4. Now I can go ahead and multiply. So let me change the colors here. All right, so now I have, once I get to cycle 7, I now have read in X of n minus 1 and H1 from local on-chip memory. And now I can go ahead and multiply them together. I have to wait 3 cycles before that multiplication is ready. So now what I want to do, I still want to accumulate this multiply operation, but what I'll do is I'll use another accumulator. So I'll use accumulator number 1. So what accumulator number 1 will do, so accumulator number 1 is going to hold, this is going to hold the product of X of n minus 1 times H1, and then it's also going to keep track of H5, X of n minus 5, etc. So it keeps every 4th term in the difference equation it will keep track of. The accumulator 0 keeps track of H0, or H0, X of n, plus H4, X of n minus 4, etc. So accumulator 0 is going to keep track of every 4th multiplication. Accumulator 1 keeps track of, so accumulator 0 keeps the 1st term and then every 4th term thereafter. Accumulator 1 keeps the 2nd term of the difference equation and every 4th term thereafter. Accumulator 2 keeps the 3rd term and every 4th term thereafter. And accumulator 3 keeps the 4th term and every 4th term thereafter. This allows us to interleave the operation so we don't waste any cycles. So now at the end of all this, if you look at these instructions before they kind of get fully going into what you might call steady state, where if you go from one cycle to the next, the actual number of commands doesn't change. Oh, I should point out that this 2 vertical bars means parallel operations. And if you remember on the C6000, I have 8 functional units, so I can do up to 8 things in parallel. So when I finally get to cycle number 10, I hit what you might call steady state. So now I've got 2 loads, a multiply and an add going on in parallel. So it takes 9 cycles before we kind of get everything to the point where if we were to write a for loop, we'd put it here starting with cycle 10. Then we would do the for loop. And now you also might realize that, you know, once we get through, we get toward the end of the terms, we also have a tapering off. We also have to, you know, eventually the loads stop. So eventually we get to a point where we don't load anymore. So that'd be the end of our for loop. Once the for loop is done, we still would have to multiply what we've loaded previously, add what we've previously multiplied, and at the very end, add these 4 accumulators, 0, 1, 2, and 3, together to get the final answer. So there's quite a bit of operations here. So if you look at all that's involved with the total number of cycles. The total number of cycles, if you include all the cycles to get going, the kind of the cycles in steady state, and the cycles to wrap things up, we end up with n plus 28 cycles. So it's n plus 26 up here, and then there are a couple of instructions that have to happen before all this gets going. We have to set up the circular buffer for the storage of the current and previous input values. So if we look at all this, if I have an FIR filter of capital N coefficients, I need capital N plus 28 cycles on this particular digital signal processor to compute one output sample given a new input sample. Now this is the FIR filter, but it turns out once we have this code, we can use the same code for any sort of direct form implementation, because all the direct form implementation is the same kind of multiply-add structure. So if I look at the biquad for a second, and this will wrap up our discussion for today. If we look at the biquad, and y of n is going to be first feedback coefficient times y of n minus 1 plus second feedback coefficient y of n minus 2.
Oh, hey Brian.
So if we look at this difference equation, it's the same structure, even though it's an IIR difference equation, or for an IIR biquad. It's the same structure of multiply, add, multiply, add. So we can use the same code for the finite impulse response filter case to implement this on the C6000. So the complexity on the C6000 is the same as the complexity for a 5-tap FIR filter, because we have 5 multiply operations and 4 addition operations. So this should take, since we have 5 coefficients, it should take n plus 28. So this should take n plus 28, which means 33 cycles on the C6000. Thank you very much for coming, and we'll pick up lecture 6, part 5 in a few minutes. Thank you.